to find GCD of 111201, 1000 and 5040, 1111, 111111. Here primes and GCDs. It turns out that we can always write the GCD of A and B as SA plus TB for some integers S and T. This is in the form when we write the GCD of A and B as SA plus TB for some integers S and T. The Buildup theorem states that if A and B are positive integers, then there exist integers S and T such that GCD of A and B equals SA plus TB, and GCD of 6 and 14 equals 2, and 2 is equal to minus 2 into 6 plus 1 into 14, that is S is equal to minus 2 and T is equal to 1. We will not prove this one, but we will give an example that illustrates how you can determine S and T. So we can simply arrange this number for finding S and T. Here 2 is equal to in the form minus 2 into 6 plus 1 into 14. So here S is the multiple of A and T is the multiple of B. So here S is equal to minus 2 and T is equal to positive 1. Here you can recall that GCD of 1001 and 1331 is equal to 11. The GCD is 11 because 1331 is equal to 1001 into 1 plus 330, and 1001 is equal to 330 into 3 plus 11, and 330 is equal to 11 into 30 plus 0. So GCD is 11, and also you can simply transform in the form 1001 minus 330 into 3. We can write 11 in the form here 1001 minus 1331 minus 1001 into 1 into 3, and 1001 minus 3 into 1331 plus 3 into 1001, which is equal to 4 into 1001 minus 3 into 1331. So GCD of 1001 and 1331 is equal to 4 into 1001 plus minus 3 into 1331. So we can simply arrange is in the form SA plus TB, where S is equal to 4 and T is equal to minus 3. Here for the lemma, if A and B and C are positive integers such that GCD of AB equals 1 and A divides BC, then A divides C. Suppose A, B and C are positive integers. GCD of A and B is equal to 1 and A divides BC. So there exist S and T belongs to integers such that SA plus TB is equal to 1, and which implies that SAC plus TBC is equal to C. Since A divides BC and A divides SAC, we know that A divides C. So why do we care? Remember last time we said that AC is congruent to BC mod M does not imply that A is congruent to B mod M. Well, it turns out that in some special cases you can cancel the C out. Let A, B and C are integers. Let M be a positive integer. If AC is congruent to BC mod M and GCD of C and M equals N1, then A is congruent to B mod M. Because AC is congruent to BC mod M, we know that M divides AC minus BC, and which is equal to C of A minus B, but the greatest common divisor of C and M equals 1. So M does not divide C, and we know that M divides A minus B, hence A is congruent to B mod M. So this is the very important relation between A, B and M by using